Friends, in the last lecture we have discussed how we can detect error by using suitable coding technique. We have discussed parity check and cyclic redundancy code for this purpose. So if a frame is sent through a transmission media and if it gets corrupted because of noise, particularly because of impulse noise, then at the receiving end we can find out that some error has occurred. But the story does not end there. We have to devise a scheme so that we can recover from error. And that is the topic of this lecture, that is error control techniques. We can assume that there are two types of error. First is, first we may call damaged frame. In this case, a frame has been received in corrupted form and the receiver is able to detect that error has occurred by using either parity checking or by using cyclic redundancy code. And another possibility is, which is called lost frame. In this case, the extent of error is so high that at the receiving end the frame is not recognizable. That means the receiver is not able to identify that a frame has been received. Under these two situations, we have to devise technique so that we can recover from error. And the basic operations which are performed, which are necessary to be performed, are number one, error detection. And we have already discussed in my last class how error can be detected either by using parity checking or by using cyclic redundancy code. What are the other operations to perform? Let us see. First of all, if a frame is received correctly by the receiver, receiver sends an acknowledgement. That is called positive acknowledgement. And in short it is called ACK, acknowledgement. Now whenever a frame is received in damaged form, then the receiver sends a small frame which is called negative acknowledgement. Or it is called NAK, negative acknowledgement. Now suppose the frame that is being received is not recognizable, that is the case of lost frame, then what the receiver does? The receiver neither sends a positive acknowledgement nor a negative acknowledgement. In such a situation, the transmitter starts a timer, waits for some predetermined duration, then retransmits the frame. That means a timer is used, timer for lost frame. So either the frame is damaged beyond recognition, or a positive acknowledgement or negative acknowledgement which has been sent by the receiver is received by the transmitter in such a damaged form that it is not recognizable. In all the situations, the timer will take care of it and retransmission has to be done by the transmitter. Now, in case of lost frame, how does the transmitter know that or rather how does the receiver knows that it is the or it is a new frame or a retransmitted frame? To distinguish between uh, retransmitted frame and a new frame, another a technique has to be used. That means the frames are to be numbered. And we shall see how the numbering can be done. Uh, there are these are the basic operations which has to be performed. And if you look at it, basic idea is this: the transmitter sends a frame and waits for some feedback from the receiver. And receiver sends a positive acknowledgement or a negative acknowledgement depending on whether the frame has been received correctly or wrongly, or the frame is lost. And the transmitter resends it. And since the basic idea is to repeat a frame whenever there is error or it is lost, the techniques are collectively called as automatic repeat request technique. Or ARQ techniques. And under this ARQ technique, there are three basic schemes. First one is known as stop and wait. Second one is known as go back and ARQ, go back and all are ARQ techniques. And third is selective repeat. ARQ. So we shall consider these three schemes one after the other. First of all, let us concentrate on the stop and wait. Stop and wait technique. In this case, this is the simplest. Sender sends a frame then, as the name suggests, then stops sending and wait. What the receiver does, receiver sends a CK, positive acknowledgement, if frame is received correctly, frame is correct, or NAK if frame is in error. Now, after receiving acknowledgement, that is positive acknowledgement, the transmitter sends the next frame. On the other hand, if it receives the negative acknowledgement, it retransmits the old frame. Otherwise, if the transmitter does not receive NAK or SEK, a timer is set up, as I said earlier, and after the timeout it retransmits the frame. So sender sends a new frame after receiving SEK, or repeats the old frame after receiving NAK, negative acknowledgement, or timeout. This can be explained in this way: stop and wait. Here is your transmitter and here is your receiver. Let's say this is T, this is receiver. This is one frame, frame number 1, which has been sent, and if it is received correctly by the receiver, after some time, small delay, it sends a small packet which is known as positive acknowledgement. So this is SEK. Now suppose this particular acknowledgement is lost. So this is lost. Or let us take another one. Let's assume it sends the second frame to, and it has been received correctly, but the acknowledgement that is being sent is lost. In such a case, after sending this, there is a timeout. After this timeout, the transmitter will once again send frame number 2. That is, frame number 2 is once again sent here. So this is how it works. Let us look at the timings. This particular time, which is needed for propagation, or it is called the propagation delay. This is represented by T prop, propagation time, and this time, it is the time required to send a frame, transmit a frame. This is called the T transmission time, TT, or T frame F, frame send transmission time. And there is a small delay, as you can say, in between sending the acknowledgement frame and after receiving the frame number 1, the receiver will require some time to compute or to detect whether there is any error or not. That time is represented as T proc, processing time, and this is your processing time. Plus, there is some time required to send the acknowledgement frame. This is the time required to send the positive acknowledgement, and again there is a propagation time delay to send the acknowledgement frame. So T prop, propagation, and after that the receiver will take some time here to processing purpose to detect whether it is a acknowledgement or a negative acknowledgement. So another processing time. So these are the different components that makes the total time needed to send a frame. Now, out of these different components, this T processing and T acknowledgement time can be ignored because these times are small compared to TF and T propagation. That means the time required to send a frame transmission time, and propagation delay. T acknowledgement is small because the packet that you are sending or frame that you are sending as an acknowledgement is very small. On the other hand, the processing time is small because you are performing the computation with the help of a fast computer. So processing time is also small. So the approximate time Tt is equal to Tf plus 2 into adding these two T propagation. And this is equal to Tf into 1 plus A, where A is where A is equal to T prop, ratio of the propagation time by T F, frame transmission time. This is a very important parameter, this propagation delay by the frame transmission time, and this is defined as A, and this parameter is very important. Later on we shall see how it is important in data communication. Now so we get Tt is equal to Tf 1 plus A, 1 plus 2A, sorry, I made a mistake here. Since there are 2 here, it will be 2. So 2A. That is the time required to send one frame. Now, if there is any error, we have assumed here that there is no error. If there is any error, then this Tt is equal to Tf into 1 plus 2A by 1 minus P, where P is equal to probability of error of a frame. From this equation we find that when A is large, that means the propagation delay is long. In such a situation, it is very inefficient. It is very inefficient, and we shall discuss other schemes where this inefficiency can be overcome. Now let us consider the frame numbering. How the frames will be numbered. We have seen here, we are sending, let's assume this is in this situation, after timeout, the frame 2 has been sent once again. This is frame 2 and this is also frame 2. Now, how the receiver distinguishes between a new frame or a transmitted frame, whether this is frame 3 or the old frame 2, to distinguish that the frames are to be numbered, and how the numbering will be done. In other words, how many bits are necessary in the frame to represent the frame number. It has been found that in this particular case, it can be done by using mod 2. So the numbering will be only 0 and 1, and that means this frame will be numbered as 0, this will be numbered as 1, and this is frame 1. So from this we find that whenever it is 1 and 1, it knows that they are same. On the other hand, if it was supposed to be 0, if there was no error, the receiver should have received frame number 0 after 1, because this is 1. Now we have renamed as 0, 1 and so on. So in your stop and wait scheme, a mod 2 numbering scheme can be used, and number of bits required is only 1. 1 bit is required to represent the number. So that way it is quite efficient. but it is very inefficient from the viewpoint of time required, because uh, whenever A is large, then there is a long time after which another frame can be sent. This is the waiting time. So how this is overcome in your go back and ARQ, let us see. In the go back and ARQ, the frames are sent continuously, and this is very popular and widely used. Is in many standard techniques. Let us see how it works. Here is your transmitter and here is your receiver. This is frame number 1, frame number 2. Frame number 1 is sent, and immediately after that frame number 2 is sent, then frame number 3 is sent, and it keeps on sending one after the other until let's assume the present frame number is I. It can send up to n frames without receiving an acknowledgement for I. That means n additional frames can be sent before the acknowledgement for frame number I is received. So assuming that value of n is equal to 7, let's assume n is equal to 7. In such a case, it will keep on sending frames until 7 frames will be sent after 1 before receiving acknowledgement. But in this case, as you can see, the acknowledgement is received here for frame number 1. For frame number 2, acknowledgement is received here. So this is 4, 5, 6. So by the time the acknowledgement is received for frame number 1, 5 frames have already been sent. Now let us consider the situation when this is a positive acknowledgement ACK. Now let's assume this is NAK. A negative acknowledgement has been received for frame number 2. So this is for frame number 1, this is for frame number 2. So frame number 2 has been received in damaged form. So a negative acknowledgement is sent. What the transmitter will do, and what the receiver will do in such a situation. It has received 3, 4, 5, but these frames are discarded. Since frame 2 has been received in corrupted form, the subsequent frames are discarded by the receiver. And what the transmitter does, after receiving a negative acknowledgement, it starts sending again frame number 2. So it starts sending frame number 2, then 3, then 4, 5, and so on. So this is your 2, 3, it received up to 6, but 3, 4, 5, 6 are discarded. And then 2, 3, these are the new frames, and fortunately here, let's assume this is a ACK, a positive acknowledgement, this is another positive acknowledgement. So these have been received correctly. So what we find here, that the receiver has only one buffer. And that is the reason why whenever a correct frame is incorrect frame is received, when a frame is in error, subsequent frames are discarded because it cannot receive out of order frame. Cannot received cannot receive out of order frame. Now, what is the penalty for that? The penalty here, you are sending, you are retransmitting some frames 3, 4, 5, 6, although they were received in correct form. So, frames are retransmitted unnecessarily in this particular case. But this unnecessary retransmission occurs only when there is error. Whenever there is no error, then what is the frame sending time? What is the time required to send one frame? That is equal to T into F. When there is no error, it can keep on sending one frame after the other, and the efficiency is almost 1. In other words, time required to send a frame is equal to the frame sending time, and that is the minimum. Now, in case of error, this TT is equal to TF into 1 plus 2AP by 1 minus. Here we see that there is a significant change here because of the probability of error. This particular part is multiplied with TF, and this value will be more than 1 because this 2A into P, although it is small, this will be this overall value of this will be more than 1. As a result, it will take little longer time than the previous case when there is no error. But still, it is much better than the previous case where in stop and wait ARQ. In stop and wait ARQ, it was TF into 1 plus 2A. Here you are multiplying with factor P, and as you know, the value of P is equal to quite small, usually 10 to the power minus 4 or even less. So whenever you multiply by this factor, this particular part will be significantly smaller than the part which is 1 plus 2A. So even when there is error, small number of errors, this is efficient. Now, what should be I should tell about the timer out. How to decide the timeout or the timeout time of the timer? This should be greater than Pf plus 2 into P propagation. The reason is, we have seen that this is the time required to send a frame, and these two propagation times are needed, one for sending the frame, another is for sending the acknowledgement. So this is the minimum time which is necessary, or which for this duration the transmitter must wait before retransmission. So the timer can be set with this minimum value, but it can be little longer depending on the variable delay of the frames. Now, what should be the frame numbering? In case of your stop and wait ARQ, we have seen that we can use the value of modulo 2, that means the m is equal to 1, m is equal to 2. So you have only 0 and 1, those are the frame numbers. And what is the frame numbering that can be used in this case? If n is the maximum number of frames that can be sent before receiving an acknowledgement, then it has been found in case of go back n ARQ, the maximum frame sequence number will be equal to n plus 1. That means m modulo m should be equal to the will be equal to n, where the number of frames is 0, 1, 2 up to n. That means if n is the window size, then the modulus should be decided by n, where the number of frames is 1 plus 1 to 1 up to 1, 2, 3 up to n. That means n plus 1. That means 1 more than the window size. For example, say n is equal to 7. Window size of the transmitter is n. That means n frames can be transmitted before receiving an acknowledgement of the present frame. Then the m is equal to 7 and total number of frames is 8. The number of frames is 8, 0, 0, 2, 3, 4, 5 up to 8. And number of bits required is equal to 3 to represent the frame number. So with a window size of 7 of the transmitter, or the value of n is equal to 7, the number of bits required to represent the frame number is 3 bits. Now we have seen that the go back n ARQ has the limitation of resending some of the frames which were received correctly by the receiver. Say in this case 3, 4, 5 and 6 were received correctly. In spite of that, the transmitter is forced to send again starting from 2 from here. The reason was the receiver was having only buffer. How that can be overcome? This can be overcome by having one buffer, more than one buffer in the receiver, using the selective repeat scheme. Selective repeat ARQ scheme. What happens in this case? Suppose this is the transmitter and this is the receiver. He is the receiver. So let's assume the sender A has sent 2, 3, 4, 5 and 6 frames, and receiver has sent a 2 for NAK, no acknowledgement for 2. That means frame number 2 has been received in corrupted form by B. In case of go back n ARQ, the receiver will be, the transmitter will be sending since 2 is in error, 2, 3, 4, 5 and 6. All the frames are retransmitted. So these are the retransmissions. Now, what happens in case of selective repeat? In case of selective repeat ARQ technique, the this is your sender A, this is your receiver B or the other station B. Under the same situation, it first sends 2, then 3, then 4, 5, 6, and in the meantime NAK2 is received. This is your negative acknowledgement. That means 2 is in error. So only frame number 2 is sent after 6. So we find that only that particular frame which is in error is retransmitted. So retransmission is only 2, then it sends frame number 7 and so on. And what is the advantage or disadvantage of this? First of all, in this case, this is your selective repeat. Only frame in error is retransmitted. As a consequence, it is more efficient than the go back and ARQ, because in go back and ARQ efficiency decreases in case of error. When there is no error, it sends continuously, but when there is error, efficiency degrades. But in selective repeat ARQ, the efficiency is improved only by sending the frame in error, retransmitting the frame in error. Now, what is the extra overhead for this? In this world, there is nothing is one-sided. You have been achieved a better efficiency, but you have to pay some price for this. What is the price for this? In this case, first of all, we find that we are receiving frames out of order. That means 2, 3, 4, 5, 6, then 2, then 7. That means 2 has been received out of order in this case. Frames have been received out of order. How do you take care of it? We can take care of this situation by having buffer in the receiver, by having more than one buffer in the receiver. That means we have to keep frame 3, 4, 5, 6 in a buffer so that we can reinsert, we can insert 2 before 3 to construct the original message comprising several frames. So we require more number of buffers. Not only that, we have stored the frames one after the other in the buffer. We have to reinsert the frame in appropriate place. So we shall require additional hardware or software so that the out of order frame can be properly reinserted. So extra logic in the form of hardware or software for inserting out of order frame in proper place. So this is the extra penalty that you are paying, and obviously your efficiency is very high, and frame transmission time TF, TT, the time required to send a frame is very close to TF, the time required to send only the frame. That means the rate at which the utmost at the rate at which the frames are coming, you are sending one after the other. And finally, what should be the possible number of or rather the the numbering. Here, what you have to do, you have to use a modulo m which is greater than 2 into n, which is the window size of the transmitter. That means the number of bits that is required will be 1 bit more than the go back N ARQ in this particular situation for representing the frame numbers. So friends, we have discussed 3 techniques for error control or ARQ techniques, and we are finding that go back N ARQ is widely used. Selective repeat is an enhancement over go back N ARQ, but it is not as popular as the go back N ARQ. So combining the error detection and the ARQ techniques, we shall be able to transmit data error free through a error prone medium. That means we shall be able to transmit reliably through a unreliable medium. That is our basic objective of this error control technique, and we have discussed how it can be achieved. Thank you.